Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this next lecture in this particular course on analytical spectral microscopy applications of inorganic compounds and nanosystems. We have gone through a good through of this particular course. Started with some analytical techniques wherein we have gone through the atomic absorption, including electrochemical, magnetic data. So several of these topics. Then we went through a host of spectroscopy techniques, a large number of spectroscopy techniques. I'll bring the recapitulation of this towards the end of this particular course. And then lately I have done the diffraction technique also. And the last topic that we will be focusing in this particular course is the microscopy. So that will cover the analytical, spectral and microscopy techniques. And as you have noticed that I have been covering all the inorganic kind of an examples, not all the examples, the inorganic related and the nanosystem related. And that's what basically the title and try to do. And in a more analytical manner, understanding and trying to do some homework kind of thing, all these have been a part of this particular course and continue to be. So let us now as the last topic of this course, let us look at the microscopy techniques. So in the microscopy techniques, obviously we are going to look at primarily the electron microscopy and things like that. We'll tell you in a while. And again, we will look at the applications towards the inorganic or nanosystems of this. Okay, so when it comes to the microscopy, we know very well, we use every day the microscope to increase the size of the object so that we can see better. So there what is happening? The light is incidented on the object and the light reflected is collected through some kind of a lenses. The lenses where you get your magnifications and then you see a bigger. So how big you can do? Something like 1,000 times or so. So if you have something like 0.1 millimeter or something, you cannot, or much lower, like a nanometer or something, you cannot. If it's something like a millimeter or a fraction of a millimeter, yes, you can. So this is basically the light microscopy where one uses the thing. Of course, we will not discuss much in this particular course on the light microscopy because we are concerned with the systems of the molecules. The molecules are the atomic size, nanometric size. So atom and nanometric, and if you look at the layers, they could be in the micron size. So your studies are going to be more to focus towards the atoms, angstroms, nanometers and micron, but not the millimeter or higher. So that is where we are going to look at the techniques which will give a magnification much beyond that the light magnification that you are looking at. So needless to say that the microscopy is the kind of a technique where you use the magnify the object to see with more clarity. And with the advent of the recent techniques in the electron microscopy, now this has gone to the world of the biology where things are very small, a nanometer size, a micron size, a cell is in a micron size, less than a micron size, and a molecule is a nanometer size like protein, etc. And of course small molecules are angstrom sizes. So all of these, and this has revolutionized both the science and technology, and that revolutionized medicine, agriculture, environment, all these kinds of things. So there are a huge variety of microscopy has emerged in the past 5 to 6 decades or so, and more so in the past 3 decades. A large expedited manner the things are going on in the past 2 to 3 decades or so. Okay, and so therefore, just to give a kind of a introductory aspect, as you can see on this slide, the optical microscopy, as is mentioned, it is using the light and using the lenses which you have studied in your 7th and 8th standard, where you can make the focals, etc., and then you can use the magnifying lenses as well, and the light radiations. So visible light radiations basically. So you have an object, visible light, and then the reflected lights. So you will be focusing and then magnifying and then looking at the image of that. So that's what you can generate the image. So that's what is optical microscopy, and variety of optical microscopies have been developed since the optical microscopy is there, maybe some 70-80 years, even 1 century old, and then developments have taken place over the century, of course, even though the principle is that. So huge number of techniques like bright field, dark field, illumination, fluorescence, phase contrast, confocal, deconvolution, variety of these kind of techniques have been developed. Very similar analogous techniques have also come to the electron microscopy. You will see some of those as we keep moving across this particular thing. But there are a huge amount of limitations are there. One is this can magnify to only maximum of 100 to 1000 extent. So which means a molecular level, a nanometric level things cannot be visualized, cannot be imaged with these things. And this can be good for the darker objects and with which refract much better. Okay, and there's a lot of light interference will be there in these things, and light diffraction will also be limiting. So there are a lot of limiting factors in that. So therefore, using the light, optical light, you cannot see the molecular objects, molecular size subjects. So like molecules, the macromolecules or the cells, you cannot see by that magnification of that. Other thing is that they are in the nanometric size, so their wavelength, the visible light, is much greater than 500, 600 nanometers, whereas these are a few angstroms to a few nanometers. So therefore, even the light radiation does not make sense for bringing any kind of a microscopy imaging if you use for a nanometric systems like molecules, cells, and organelles, etc., all of those. So this has brought in the kind of a need where you can have the roughly a wavelength match with that, as well as the magnification, both of these. And that is where the electron microscopy comes into picture. So, and in the optical microscopy, you have the usual lenses, it's called the optical lenses, and whereas in the magnetic, the electrons, because electrons are charged and they have the magnetic effect on their things, so therefore magnetism control kind of a lenses, because they have to take care of the charge as well as the magnetic field of this. So the magnetic controlled kind of a lenses, and that will bring the additional magnification as compared to the usual light magnification by another 1000-fold. So use the light itself brings the 1000 and another 1000, so there will be 1000 into 1000, a million, but still you require much more than that. So a little bit more than, much more than million or several million will make the smaller objects to be seen, to be imaged. So that is where the electron microscopy into that. So this one of them in this where you use obviously the electrons, and later on I will talk to you when the electrons incident on the matter, what happens, how happens, and what we will look at. All of those will come after a while. But right now we will look at some other basic aspects of this. So with the electron microscopy, as I mentioned, you can increase the magnification by another 1000-fold, bringing an overall magnification of 1 million to 10 million, and at times even 100 million range of increase in the magnification. Of course, not only magnification, you also need resolution, very important. So what you're measuring and what is the difference? So the energies, obviously electrons energies, therefore they are measuring some energies, and the difference in energy. So difference in energy by the total energy, that should be as low as possible in order to get your resolution. So one is magnification. Suppose you magnify but it's blurred, there's no meaning, so you cannot get an image properly. So you magnify but you don't blur it, but you get a clarity, then you have a meaning of that. So that is where, so you're looking for the electron microscopy not only to magnify but also to resolve the thing so that you get a proper image, so that you can map, you can see the surfaces, you can see through the material, of course thin layers, etc., and structures and many things. So therefore you can do many other technological advancements can be utilized using those things. Okay, so one of these is the electron. When you impinge, one is it can just reflect from the surface itself, okay, and the other one is it can pass through and come out of that. So one is the transmission, when it passes through and then comes out. If you have a compound, a molecule, or as a layer, and suppose you are being electrons, so the electrons can get reflected, scattered with a very little inside, it goes into that, okay, or they can come, pass through and then come out here as well. So therefore this is the transmission transmitted electrons, and these are scattered electrons. Okay, so you can measure this, you can measure this. So these are all, you are playing with the energies of very high energies, etc. Of course energies will differ a lot, I will come to that. So therefore this kind of thing will come in transmission electron microscopy, and this one will come in scanning electron microscopy, and the short form is used, scanning electron microscopy, SEM and TEM. I will not use the word SEM and TEM, that's not a very nice way of using that. Kindly use SEM and TEM. Okay, the short forms of SEM, TEM does not make too much of a sense. At times you lose the meaning and relevance as well. Okay, so SEM, TEM spectroscopies. So these are using the electron. Now using this electron, you can get the magnification further by 1000 to 10,000, and resolution is also important. So as I said, if you don't resolve and only magnify, it becomes a blur. There is another spectroscopy, microscopy, which is also used, which is, suppose you have a surface, so you just touch the surface and try to see what is there on the surface. So instead of passing through or reflected electrons, you will have some sensing element which will keep touching or close to touching and then move across the x-axis, y-axis and z-axis. So this is what is called the scanning probe. So you will have some probe here, and this probe will be moving along with that. So this is, let's say, a probe, and this will scan in all these directions, x, y and z directions. So this is scanning and probing, scanning probe microscopy. So this is where the thing is. So in this, so what we see is atomic force microscopy is one of them. So this will not use any energized particle. It will have only some touching nose, and that touching tip or the nose will keep touching the whole surface and then bringing the information on that. So that is why it's called scanning probe microscopy. It is a probe, so it probes certain information, some forces, and it scans and it gives an image. Microscopy. So microscopy is an image. Okay, so that is where in that a specific one is atomic force. So you're looking at the atomic forces. When the tip, what kind of a forces are there between the tip of the probe and the surface layer of your molecules, of your atoms, of your species. So all of these, and so they will chemically differ, they will structurally differ, they will differ in terms of the surface topology. So you can get all of those features from the atomic. So here you don't use electron, you use just some kind of a metal based kind of a tip, which I will talk to you a little later about that. So it instead of seeing, it touches and feels and then gives the information. What it feels, it gives the information to the receiver, and from the receiver you can get the data, and then clubbing the data you can get the picture, and that means you can get this image of that. So there are variety of these things. There's scanning probe microscopes, so they will give more accurate picture, the nanostructures, surfaces, and even the properties information also. Like some of the materials are hard, some of them are soft, some of them are high elastic, some of them low elastic, all these kinds of things. So you can get about the material. So the properties, surface, topology, so all these things are kind of. And if you change the chemical species also, and then the probe movements will also change, the probe reactions will also change, the probe outputs will also change. Therefore you can see something is different than the other. So the force between that species, between that atom, between that surface and the tip. So therefore that is scanning probe microscopy, in that you will use that. So we will be studying in this particular topic basically the electron microscopes and the scanning probe microscopy, and in particular atomic force microscopy. As I said, that there are a huge variety of these probes. By varying the probe, by varying the measurement, this technique will vary. But overall, the technique has the same principle. So the principle does not vary, but the functional aspects and the probe, etc. will vary in that. So before we go to the electron microscopy, let us start with the scanning probe microscopy, which in specific is the atomic force microscopy, and which is referred as the AFM. Okay, so as I just now mentioned to you, atomic force microscopy is something like where you have a probe, which touches the surface and tries to find out. So when it touches the surface, there's some kind of an interactions working. So between the probe and the surface molecules, surface atoms, surface species, and that kind of a thing. That okay, this will give basically a feel of a touch of the surface. So you can study a lot of parameters, and mechanical is a kind of a mechanical probe, and so you can use some kind of a piezoelectric kind of a connectivities to this probe, to this technique, and therefore you can use variety of methods, which I will come a little later, what kind of a methods you can use. So with this you can get a resolution of atomic level or angstrom level resolutions you can get, and you can get much greater than 1,000 times more magnification than the optical. So all these kinds of things can be there. So you will not be using any of the electrons, energized particles, etc. in this. Okay. So you use that tip. Only thing is you need to control the tip's movements. That's what is important. And that's what we will learn as we keep moving across this particular things. So this is basically the atom force but not the nuclear forces that you are talking about. So this you require a very precise geometry, precise electromechanical movements, so which is the piezoelectric based ones. Then you need to move either the probe or the tip or the sample in the different directions, so that you can get into X, you can get into Y, you can get into Z, so that you are walking on a surface kind of thing. And when you're walking, you face certain reflections, certain attractions and repulsions kind of thing, pulling the tip closer, pushing the tip farther, and these kinds of things. That is what gives you the surface topology, the shape, etc., all of these. So in particular, the AFM has three major abilities: the force constant topography of this, the measurement, the topographic imaging, and the manipulation of the tip or the manipulation of the surface. So this kind of a manipulation methods. So the force measurement, and combining all these force measurements, you can get the topographic imaging, and you can also manipulate and try to understand this. So what is the force measurement? So the AFM can be used to measure the force between the probe and the sample. Okay, so as a function of their mutual distance, mutual separation. So let's say this is my probe and this is my surface and this is my probe. So either the surface will be moving or the probe will be moving. You can do either way. You can do both of them also. And what you need is relatively how it is going. Suppose if I have here going this way, if I have this again going up, again going down, etc. And it's not just the physical going, it's the chemical interactions also are important between the atoms that represent, etc. So as a function of this one. So this can be applied to perform the force microscopy to measure the mechanical, the properties of the sample like Young's modulus, etc. So what kind of forces? I'll come in the next slide and I'll explain you. Just hold on till then. Just giving you a basic, the feel first, and then give you a little bit more depth in the next. So is the forces that you're going to measure. Then the second point is the topographic imaging. Okay, so that is because when it moves, there is a reaction between the tip and the surface. Okay, and because of these forces, and that reactions you're measuring in the form of some kind of a signal. Okay, that could be a deflection, or you fix the movement of the scanner or the probe, and how much of the feedback power is required to control. You can use that also, or you can use the deflection, or you can use the displacement. Many of the techniques are possible, many of the parameters are possible, and the techniques are already developed by the engineers to make the technique more workable. Okay, so this is basically done to get a high resolution surface by the raster scanning, because you do by the line by line, the close kind of things. That is what the raster scanning at the position of the sample with respect to the tip, and the recording the height of the probe that corresponds to a constant probe sample interaction. So either you can keep the interactions fixed and the probe movement, or you can make the interactions as it is and keep the probe constant. So all these kinds of things. So you can measure the deflections, you can measure the feedback power, etc. all of this. So third point aspect is, so that is how you can get the scanning of the whole thing, and then that connecting the whole data will give you a picture of the topology or surface image of that, and then surface contrast can be made clear by using certain kind of colors, and those are all there in the programs already. You don't need to worry about it. Third aspect is the manipulation, the forces between the tip and the sample, or you can modify the tip or you can modify the surface. Modify the surface means you change the compound from one type to another, which is embedded with something, or some atoms are changed, some species are changed, etc., or thickness is changed. So variety of these parameters can be changed and then studied. So you can manipulate your surface, you can manipulate, or you can just etch the surface and do it. So variety of these things. And in some cases the metal foils will get a little bit rusted, then you can remove that, or oxide layers, you can remove that and study it, leave it and study it, all these kinds of things. Then the tip can be modified chemically. Also, the tip you can put certain kind of the atoms or molecular layers which will have some specific interaction with your molecule which you're studying also. For example, if you're using an enzyme layer, and you can modify the tip with certain small molecules which can act like a substrates. They will identify the reactive centers in your proteins, in your enzymes, etc. So like that. So, or enzyme substrate interactions, or enzyme inhibitor kind of things. So variety of these things, enzyme substrate. So you can, or you have a cells, a layer of cell. Now you want to study the cell surface has got a lot of molecules which are called receptors. Then you have certain small molecules which are received by those receptors. So you can modify the tip with those molecules so that the cell surface can be recognized. So therefore you will have again. So such kind of molecules will also help and include atomic manipulation or the surface manipulation, molecular kind of manipulation, scanning probe lithography, and local stimulation of the cells, as you mentioned, examples as I said. So variety of these things. This is just not limited. Okay. So overall, the atomic force microscopy to the scanning probe microscopy, it just not only measuring the surface parameters of the topological image, but also you can get the other properties of the material. Okay. So use that material, the properties, as a function of the surface, as a function of the xy, as a function of the z profile, etc. You can get those data and then find how such properties are distributed in the surface. So those properties may be required for you for some purpose, for some application. So therefore you need to map those kind of things. For example, mechanical properties like stiffness, adhesion strengths are these. Some electrical properties you want to measure, or conductivity properties, or surface potential properties. So using the AFM with some modification, you can call it as SPM. SPM is a host of techniques of all AFM, and that contains a conductivity measurement, a force measurement, an adhesion, a stiffness measurement, or surface potential measurement. So all of these. So different kind of fields, and engineers using different kind of materials use different kind of techniques. So people who are working in electronics, they look at the electrical conductivity and the surface potentials, etc. The people who are working in conducting physics and conducting materials, they use the conductivity. And people working in mechanical side, they will use the adhesion properties, stiffness properties, etc. So all this. And the physicists, chemists, biologists will use for their molecules, for their systems to probe, etc. So it's a host, it's a big basket of techniques. This overall techniques are called scanning probe microscopy, of which atomic force microscopy is one such technique which uses the force between the tip and the. So tip should not be taken just as some kind of a inert kind of a material, but it gets reflected, deflected, etc. in that too. Just look at before closing this particular lecture, let us look at the principle, the configuration, and the function of it. So as I told you, that you have a tip or a probe, you can call it as, and this probe is the one which will move on your sample, or the sample can be moved, and then there will be deflections. So to understand these deflections, you need to have some light reflected on that, incidented on that, and based on the movements, the reflection or the laser will change, and the angle will change, the strength will change. So all of these you can measure. This is what you call it as a photodiode, and so detector, and that is connected to detector. Okay, and this will have the sample surface to this, and this will measure and give you the in terms of the photons, etc., photocurrents, etc. you can make. So what should this kind of a machine should have? A micro kind of a tip. Okay, so this is what is called the probe. You can call tip, you can call probe. both ways. And the tip you cannot handle with hand, you cannot move, so you need to be connecting to this. A particular thing is a cantilever support, okay, and this cantilever support is this is a cantilever support which is connected to this one, and this is by the piezoelectric element which will make the movements between them, okay. So a spring like cantilever, and then you have a support, you have a piezoelectric element, you have the tip or the probe. This is one set of the things. The other set is this one, which is the sample bed and which is a sample, and this is some system which can move the sample in the x direction, y direction and z direction. So that can give you all three directions here. So this can bring a kind of movement in this direction, and movement in this direction, movement in the up and down. So it can be in this, it can be in this, it can be in this. So you can probe both the x, y, all the three x, y and z, and some kind of a detector. Of course, other connections are not shown for simplicity. So this is the basic principle, and this is the next level where the instrumentation kind of thing. So the interaction between the tip and the sample at the atomic scale. Now you're going by very slowly. You're not running like mad. You for second you will scan something like a few angstroms to a nanometer or so. So slowly you scan across it, and you know the size of this tip is just a few nanometers to nanometer size kind of thing. So nanometric scale interactions. So this transduced into the changes the motion of the cantilever, and this measures the quantity of interaction, as I mentioned. So that can be measured in variety of ways. So one is by deflection, other is by the movement, other is by the feedback control, other by fixing the force and the feedback, or allowing the movement and fixing the force. So all these kinds of things you can use. So different the techniques of the SPM, different of these methods are used, okay. So you can scan the x direction, y direction, z direction, therefore you can get a profile of the surface. So therefore that mapping will give you the corresponding the image of that. So I think we have come to somewhat very fundamentals, introductory and the basics of the AFM, and we'll keep moving across this particular course to the AFM examples, then TEM, then SEM, with the principles and the examples as well, and in that manner. So thank you very much.